So our final area of experimentation was cloud. Cloud's a hot topic nowadays. So everybody's looking at moving a lot of their services and architectures to the cloud. So we wanted to begin the process of looking at how OGC services and architectures work in that environment. So we started with some very simple experiments and working to create increasingly complex approaches. The simple experiment we did was just put services on the cloud, look at scalability and performance. What's happening? Clearly, a lot of people move to the cloud because you get cost benefits. You don't have to manage your own infrastructure when you have heavy loads, like in an emergency response disaster situation, which a lot of geospatial people are interested in. You might have amazing intense load for a month, and then certain services might not be used for years afterwards or before. So the cloud is a perfect environment for that. So I wanted to see how OGC services did. Another important aspect for the geospatial industry is processing on the cloud. We have huge data sets, but our computational processes are usually very small code. You know, if you write any software program, even a 1 gigabyte software program, even that's much smaller than data sets often use, which could be multiple terabytes. So being able to move processing to data is a place we want to get to in OGC. And the interoperability angle here is highly important because often you want to move processing to data which is housed by a different organization, potentially a different software environment, potentially a different cloud provider itself. So looking at all these different hybrid scenarios were of interest to us in this and future test beds. So we have come out with a performance and scalability engineering report, which does some of that basic, gets some of that basic information out about the ability of OGC services to perform well in the cloud. We're lucky to have Amazon Web Services participate in the test bed and help us out with some of this work. And you'll see in that report reports on or statistics on web mapping services and web map tiling services and how performance works on, in Amazon's case, S3 versus a simple EC2 server, which is basically their name for just a regular virtual server, basically another, looks like a computer out there in the cloud, versus S3, which is basically a file storage system, which can be used to mock up a WMTS. So you'll see some discussion of that in there. You also see a section of that report done by 52 North, which talks about a hybrid cloud setup, benchmarks against quality of service requirements of the European Inspire project. And there's some interesting processing scalability results in there. You'll see the graph at the bottom left of this page, talking about the average time of the WPS to respond. I'm sorry, that bottom left graph was GMU and other participants' work on benchmarking computational services. The the work done by 52 North about quality of service requirements of Inspire is also in the report. That's just not the graph. So that's the performance and scalability engineering report we worked on. The final cloud area, as I mentioned, moving processing to data, I think is the big thing we want to get to as far as interoperability goes. A very hard problem to approach, and we had some great European experiment in this project. And clearly there's some great solutions out there, but still more work to be done to really have a generic and interoperable cloud processing. So let me briefly describe this, one of the experiments this group of participants did. So here we have, what you're seeing on this screen is a hybrid, very complicated hybrid cloud processing scenario, where if you look at the bottom of the graphic where it says Terradue 2.0, you have an orange box with some white squares in there. So what you're representing there is a cloud marketplace. This is a place where you can You use a CSW server to search for data sets, search for computational processes you want to use, and which are which are actually web processing services. And so once you do that, you can, purchase or acquire things in the marketplace and then decide to run services, actually execute the what you want to have done. So in this case, Terradue and Geomatis and MapShop and Kines worked on a project for running an SBAS process. SBAS stands for SBAS interferometry. SBAS stands for small baseline subset, and basically what the process we're talking about does is find areas which may be prone to earthquakes. So what happens here is that you identify your data, you identify the SBAS process that you want to run, and then you deploy this process to either that cloud or another cloud. In this example, if you follow the gray arrow on the left, that SBAS process gets deployed on an Amazon cloud in Dublin in the UK. But actually, we have data on another cloud over there on the right. So once the process gets deployed in a cluster over here, in this case, I think the data is coming into or over to the cloud of the processor, and it's running its processes and returning information back to the client without ever going back to the first cloud. You could also move the process to the data in certain scenarios where that's important and still get back the result to your client. Now I'm going to wrap up with a final cloud scenario where we look at a land cover image processing application. So this is showing you a bunch of different steps. The purpose is to ortho-rectify imagery and do some quality assessment of its ability to do land cover classification. So here we're picking an area of interest out of a raw satellite imagery that's not rectified yet. So this is the area we want to work with. It goes off to a web processing service to get ortho-rectify, and you saw it turn, so it works to the ground. And then that imagery is downloaded. Now, that's great in and of itself to have an automated ortho-rectification process. But let's look at this, how well that ortho-rectification was done. And this is another web processing service which goes in, looks at the quality of that ortho-rectification, shows you the errors where it might not be so accurate. Okay, so let's say we did a great job ortho-rectifying that imagery. Now let's move on to the land cover classification step. Here you see a nice graphical interface for training the process. Often with land cover classification, you want a human to say which areas are trees, which areas are water, which areas are field, and you just pick a few of those, and then the computer can do the hard work of finding those all over the place. And there you see it go off and do that, and you have a nice full process from end to end of being able to do ortho-rectification and land cover classification, all through web processing services in the cloud.